All right, everyone. This is it. End of the road. Our final, we already talked about that, right? I want to kind of get this stuff out of the way so we can get down to business. Our final is on Wednesday, 12:30. You are allowed to have on that, for that final, you're allowed to have everything, all the formula sheets that are on our Canvas page. Under files, it says formulas you can bring to the exam. So everything here, I even put what I sent out in an email on Monday. That's available to you. You'll have to print those out, so it's going to be like 30 pages of stuff, but you can have all those. And then in addition to that, I'm going to allow you to create your own formula sheet. You can just use a standard sheet of paper, whatever you want to put on there that you think will help you on the test. You just cannot have worked out problems. Okay, so you can't just have like examples worked out. You can have steps and procedures, anything that you think might help guide you through certain things, but you'll be showing this to the camera and you'll also be turning it in with your work. So just to make sure everyone's playing by the rules. And yeah, any questions about that? So I would like to see if it's possible to let you use your computer during the test to be able to look at the test or look at the, well, not to look at the problems, for the formula sheets. I know some of you may not have printers. So what I'll say is you can reference your formulas on your computer screen if your camera setup can see the screen and you. So the camera that you're using for the test would have to be somewhere like behind you to the side, so I can see your work area and I can see what's on your screen. If you can get your camera set up that way, then I don't mind if you use your computer to just look at formulas. If you're like doing anything else, Wolfram Alpha or anything like that, then that'll be like you're cheating, okay? So if you can do that, great. If you can't, then you can't have your computer on. And then what I'm going to do, since you all have the review, all right, since you all have the review, I'm just going to tell you, okay, I want you to do number whatever, I'll tell you which of these I expect for you to do for the final. All right. Any questions?
Are we allowed to have a basic derivative and integral sheet? Because I've got forgetful memory and I forget basic derivatives and integrals.
That's part of what's on here. Part of these formulas are all here. All those are here, derivatives, and here are all the derivatives and then all the integrals. Yeah. So, yes. Okay, down to business then. Yeah. All right, so last class, we had started talking about surface integrals, and we had done surface integrals over scalar functions, and I'd given you that sheet that had the special cases. We had talked about these different cases when you're doing surface integrals, and that if you just know how to draw the surface with some vector function, then here's what you have to do a surface integral. But there were three special cases in which your surface was a function of x and y, or if your surface was a function of x and z, or if your surface was a function of y and z. There's these special cases, right? So we did that last time. And then we started talking about oriented surfaces. And the fact that when you have a surface, you have this concept of normal vectors pointing out from the surface. And I want to just illustrate that again for you because it's going to be important today that you kind of grasp this quickly. If I have a surface where this surface is z is some function, I'm going to call it g, some function of x and y, then it's a sheet that's floating in the wind like this, where the domain is on the ground. Then if you take any normal vector to this surface, and so the normal vector would be pointing perpendicular to the surface, no matter where I am on this surface, okay, doesn't matter where I am, do you all agree that the z component of all of these vectors must be a positive number if they're pointing up, right? Then they would be all positive. Now the x and the y components might be, positive or negative, but the z has to be pointing up if it's if it's going away from the xy plane. Now, if you look at that normal vector pointed in the other direction, it would still be perpendicular. It would still be considered to be a normal vector, but now the z part is negative. Do you all agree? So for any function of x and y, we know something about the z component of the normal vectors. They're either positive, pointing up, or they're negative, pointing down. Agree? Those components. And the same can be said for if you have, let me do another picture here. If you have a surface that's like over here, where the domain goes to the yz plane. So in other words, your x is some function of y and z, then if you look at the normal vectors here, what can you tell me is always positive or always negative? What component?
The x component.
The x component, right? So for all of these, the x component would have to be positive, or if we went the other direction, the x component would have to be negative. That making sense? You'll see why this is useful in a minute. And then the last case would be if our surface was like over here and the projection to the domain was onto the xz plane, then this y would be some function of x and z, and then the normals would all have a y component that's positive. Or if it pointed the other direction, then it would have a y component that's negative. Yeah? Okay. So this idea of oriented surfaces is that anytime we have a surface, right, we should have normals that point in one of two ways, right? With a sphere, you could say that normals point in, or you could say normals point away, right? From this ball, kind of the sphere. But if it's just a sheet flowing in the wind, then that's a little more general, and it's harder to say like what's positive and what's negative. So when we look at these scenarios, when we look at a sheet like this and we say the normals are oriented positively, we mean that it's pointed up. Negative orientation would be pointed down. Here, positive orientation would be pointed down the x-axis. Negative orientation would be pointed in towards going into the x-axis as opposed to out. And then same thing here, positive would be to the right and negative would be in. So that's just so we make sure we understand orientation of surfaces when we say positive and negative, what I mean. Is that clear? Questions? Okay, so we talked about oriented surfaces, and then we talked about, well, how do you compute the normal vector for a surface? So if you want to compute the normal vector for a surface, you have to do that computation. And we talked about that in the previous class, where you just take the two partials of your vector function, cross them, and then if you divide it by its own length, then this normal vector not only is perpendicular to the surface, but it also has a unit length. So it's a unit normal vector, length of 1. All right, and then we finally got to this, and this is where we kind of stopped. And I was trying to explain to you what flux was. And so that's what we're going to pick up today. When we're trying to calculate flux, this is the notation we use for flux. It's the double integral over some surface of a vector field dotted with ds, where s here is a capital S with a vector. What does that mean? it means, like I said before, we're going to take these, we're going to take points along some little patch, and then we're going to take the vector field coming out. We're going to take the normal vector. We're going to project the vector field onto the normal vector, and then add up all of these flows out of this patch. And that's what flux was. I already showed you this, but this is the notation for that. And then here's the actual computation that we have to do. It's a double integral over the surface of f dotted with the normal vector. So we're going to dot the field with the normal vector ds. This right here is this double integral over s ds is the previous part of this section. Okay, that's 3.7. That's earlier when before we had vector fields. And I want you to notice that f dot n, when you take a dot product of two vectors, you get a scalar, right? So when you dot those two, you're going to get a scalar function, which is going to be like the problems we were doing before, like this problem. Okay, it'll be like that. So we're going to wind up doing surface integrals, but rest assured that this in here will be a scalar function. Now that's one version of it. If you want, you can then convert that surface integral into a double integral over d. So that's a double integral back from earlier in this, what chapter is that? Chapter 12, I think. Just a standard double integral of f dotted with the not the magnitude of f dotted with the cross product of the partial derivatives of the surface, that the vector function that draws the surface. Okay, we're gonna need all this. All right, I'm gonna just copy this down. Let's just get to an example. All right, so we want to find the flux of this. Let me get to a new page. Let's get these formulas here. Let's get that problem. Okay, so find the flux of the vector field F equals YZX. So this is kind of like, yeah, okay, this is our vector field. Normally we call this like the P part, the Q part, and the R part. But this is our vector field, and we want to do it across the unit sphere. So you need to know how to draw the unit sphere using a vector function, which we've done already. So I'll remind you that to draw the unit sphere with a vector function, it's r of uv equals, normally it's rho, but it's the unit sphere, so the radius is 1. So this should be sine phi cosine theta, sine phi sine theta, cosine phi. So we did this, let's see, here it is right here. This is it. Oh, sorry, I'm using theta. I apologize. I'm using theta and phi. I should probably make this u and v just to be consistent with what we did before. I apologize. So to be consistent, so we're using the same notes as before. V was our theta and u was the phi. So u, v, u, v, u. So v went between 0 and 2 pi, and u went between 0 and pi. So that should draw us our unit sphere. Okay, next thing. I'm going to need to cross the partials. Okay, I'm going to need to cross the partials. Now, again, we've done that before, didn't we? Didn't we cross the partials before? We took the partials, we crossed them, and this is what we got right here. I'm going to just copy this if I can.
Sorry, sir. I thought it was V was. Oh, no, never mind. Sorry.
You sure?
Yeah. I see. It's correct.
Yeah, okay. So I'm going to take this. Here was the cross product. Now I need to take the r's out of there. This is partial with respect to u, cross partial with respect to v. Let me get the r's out of here. Okay, so there it is right there. Okay. So that's our cross product. So what we're supposed to do is dot that with the vector field. Now, what do we mean the vector field? We mean the vector field evaluated along the curve. That means we want, this notation really means take the field and evaluate it along the actual surface, not curve. So I'm going to take this vector field and I'm going to replace y with this, z with that, and x with that. So let me go ahead and write down what that is. F evaluated along the vector field or along the surface should be the y, which is cosine u, the z, sorry, I wrote the wrong thing there. Sine u, sine v, the z, which is cosine u, and then the x, which is sine u cosine v. All right, so I think we have everything we need to start cranking this thing out. We want to calculate the flux, which is this notation, which is, I'm going to use the second version, this right here. So this will be the double integral over d of f evaluated along the surface, which we know was this one, this vector sine u, sine v, cosine u, sine u, cosine v, dotted with the cross of the partials, which is sine squared u, cosine v, sine squared u, sine v, and then cosine u, sine, what was that? Cosine u, sine u. I'm missing a u right there. dA. All right, let me check my work here. I worked this out before class because I didn't want to screw it up. Okay, so now yeah, let's go ahead and dot those together. You ready? Dotting them. Double integral over d. So remember how we dot? We go here to here, right? Hold on, I'm making sure I'm not missing something here. What did I put? Okay, yeah, but that should be sine cubed u, sine v, cosine v. That's those two multiplied, right? Plus now these two. So that should be, something is not right. Hold on. Let me just double check my R cross. Did I get my vector field wrong? I feel like I wrote it down wrong on my page here. So y should be this. This is just the way my day's been going. I swear it's been one of these days. Do y'all see anything wrong here? My field.
The only thing I thought was the placement of the vector in the vector field, the y, z, x. What do you have to?
So my field is y, right? It's the field evaluated along the surface. So the field is y, z, x. So the y should be the y part of the surface, which is this. That's that. And then the z should be this, which would just be that. And then my x should be this, which is that. Okay. And then I'm supposed to dot that with this. So when I multiply those two together, I get that. Multiply those two together. I guess it's right. I mean, something's wrong in my work then. My work is something different, but I must have screwed up my work. These two multiply together, right? That's this. That should be sine squared u, cosine u, sine v. And then the last multiplication for dot product should be these. So plus sine squared u, cosine u, sine v, cosine v. There. dA. All right, I think that looks okay, I think. I don't see anything wrong. I'd have to go back and look at what I did different in my work because something ain't right, but. Have I confused you thoroughly yet? Are y'all okay? Are y'all all right?
Yeah.
Okay. All right, so now we need to just figure out what our limits of integration are, but because we already know how to draw the surface, it's just right here. And the order of integration won't matter because they're both between constants. So it's just all of this. And now I'll go d, let's see, du, dv, like that. So whatever this is. So could you integrate that? It's doable, right? I mean, like we could. What's that?
It'll take a minute.
Yeah, it'll take a while to do this because you'll have to do with respect to u first. So you'll have like sine v, cosine v as a constant, but integrating sine cubed, if you go back to Cal 2, you'd have to like break this down to be sine squared times sine, turn sine squared into 1 minus cosine squared, and then do a basic U substitution. This one's a little easier to do with respect to U because I have sine U squared here, and then cosine U is its derivative, so that would be kind of a basic U sub. And then same with this one, basic U sub. So it could be done, all right? I'm not going to work through it because time. I'm just going to leave this as a dot, dot, dot. But maybe if I have time at the end, I'll come back and throw it into Wolfram Alpha or something and get an answer. I had already done that, but again, something is up with my work. My cross product is right. I don't know what the hell I was doing. I think I used a different vector field. Did I use a different? Whatever. Okay, we're going to move on. This is dot, dot, dot. There's a number. That's your answer. That's your flux. All right, let's go to a different problem. Or no, not a problem. Some special notes. Okay, so this, in the problem we just did, right? This flux problem we just did, we had to have the parametric or the vector function that drew the surface and the limits on that. And then we had to do the cross, and then we had to evaluate the field along that vector function. Then we had to dot those, and then we just grind out the integral, right? That's what we'd have to do. The formula I did not use this one, right? And I didn't use this one. The reason I didn't do this one is because in order for me to use this one, I would have to have known what the normal vector to the surface was. But the problem is that when you have a sphere, your normal vector is always changing depending on where you are on the sphere, right? So I would have had to have figured out what that is, and that would have been a bit of some work to do, all right? I would have had to have taken the cross of the partials, go back to the notes. How do you find the normal vector? To find the normal vector, you have to take the cross of the partials, which we did, but then you'd have to divide it by the magnitude of the cross of the partials. That would have been a lot of work, right? Because the magnitude is the square root of the sum of all of the pieces squared added together, all that. So I just skipped over this version of the formula because I didn't want to mess with n. Okay, I didn't want to mess with it. So I just went straight to this. Now, in the event that our surface, okay, in the event that our surface is one of those three special cases from last class. So I'm going through the things that I gave you last time. Formula E is when we're doing a surface integral over a vector field. So this is flux. This is what we just did, okay? This was the formula we just used. But if the surface is a surface where z is a function of x and y, then this entire flux integral simplifies to be this. PQR, that's our vector field dotted with the partial of g, negative partial g with respect to x, negative partial g with respect to y, and 1. And I show the work right here why it's this case. I'm not going to go through that. We're just going to realize there's a special formula when our surface is a function of x and y. And let me point one more thing out here. When we use this formula, we are assuming the normal vectors are pointing up. If we need to do the flux where our normal vectors, we need them to point down, all we will do is put a negative in front of this. Okay, so negative in front of this would give us the flux if our normals were pointed the other way. The next special case is if our surface is y as a function of x and z like this, again, with the normals pointing down the y-axis like this, then the formula becomes this right here. Okay, and I put here, we're pointing it down the y-axis. Okay, so that's the direction of the normals. That's our formula. And then the last special case is where we have our surface is x is a function of y and z, where our normals will be pointing down the x-axis like this. And that would be this formula here. Okay, so we have three new formulas for these special cases. And let's go ahead and see how we would implement that in a problem. So find the flux of the vector field xy, yz, zx across the surface S, where S is the part of the paraboloid z equals 4 minus x squared minus y squared. That's that thing. That lies above the region, x is between 0 and 1, y is between 0 and 1. So the shadow of this thing on the ground, okay, the shadow of that on the ground, oh, that's terrible. Is like that. So our x is between 0 and 1, and our y is between 0 and 1. So what you have to see here is that this z is some function of x and y. See, our surface is very special. It's not like the sphere where we had r of uv. This is a function of x and y. And because of that, what is it? It's 4 minus x squared minus y squared. Because of that, I can use a different formula than the one we used in the previous problem. So let's do it. So which formula am I going to use? I put letters next to them. So which one was it now? Is it H or G or F or E? Which one is it?
Or not H, F.
F, because our surface is a function, Z is a function of X and Y. So this is what I need to do right here. This is what I need to use. Now, I'll remind you that P is this, Q is this, and R is this. Those are the components of our vector field. All right, let's set it up. We're going to need to know the partials of G with respect to X and Y. So let's go ahead and do those also. I'll do those down here. What is the partial of G with respect to X and Y respectively? So with respect to X, it's what?
Negative 2x.
Negative 2X. And with respect to Y, it's negative 2Y, right? All right, so we're going to do double integral over D of negative P. So the opposite of P is negative XY times the partial of G with respect to X, which is negative 2X, minus Q is Y times Z, times the partial of G with respect to Y, which is negative 2Y, plus R, but R is Z times X. All of that dA. Okay. Now, this integral is going to be done over the region D, and D is the ground. So we need to figure out what our limits of integration are. Is it obvious? X is between 0 and 1, Y is between 0 and 1. I mean, that was given to us, wasn't it? But there's one little issue we have to resolve. In this expression, we have a couple of variables in here that we need to deal with. See, there's a bunch of X's and Y's, which I'll be able to integrate, but we have Z's in here too. And remember, Z was a function of X and Y, wasn't it? So everywhere I see Z, I need to go in that integral and replace it with 4 minus X squared minus Y squared. I think I'll clean it up before I do that. I'm just going to kind of get some of these negative signs and stuff out of here. This should be 2x squared y. That's these two together. This should be plus 2y squared z. And then plus zx dA. And now I will replace, let me go ahead and do my limits of integration too. 0 to 1, 0 to 1. We'll have 2x squared y plus 2y squared times z, but z is 4 minus x squared minus y squared. And then plus z, which is 4 minus x squared minus y squared, x d y dx. Doesn't matter what order you do those in. So just remember, I replaced my z's with that. And that might look bad, but it's actually not that bad because it's just a bunch of polynomial stuff, right? So we should be able to do that given enough time. See if I did it. I think I actually did do it. Yeah, here it is. I had the computer do it for me. And I got 713 over 180. So I'm not going to show that work. You would have to like distribute that x through and then collect like terms, then just integration. So again, if you're trying to do flux where the surface you have cannot be written as a function of two variables, like the unit sphere cannot be done that way, then you have to do it this way. You have to evaluate the vector field on the curve or on the surface. You have to cross the partials, dot those things together, and then do your integration. If you can actually get it to a function of two variables like this, you can use one of the shortcuts. Let's take a look at another one. Find the flux of the vector field F. Here's the vector field across this surface S, where S is the part of the paraboloid y equals x squared plus z squared with y between 0 and 1, and the disk x squared plus z squared equals less than or equal to 1 with y equals 1. And it says here, use positive orientation. All right, so here's the surface. It's actually two surfaces, the green one and that kind of brownish gold one. The brownish gold one right here is y equals x squared plus z squared, where the y value is between 0 and 1. So it's like a paraboloid there. And then the disk is the green part, which is x squared plus z squared is less than or equal to 1. And then we're fixing the y value to be 1. So that's our surface. It's both of those together, and we want to find the flux, which is basically the flow out of this thing with this vector field. So I'm going to copy this over. Let's break this down into two surfaces. All right. So let's look at S1 to be that disk, and let's let the other part there be S2. All right, so positive orientation. Think about positive orientation. That means all my normal vectors need to be moving away out of the surface. So my normal vectors on S1 are going like that down the y-axis, pointed out towards the y-axis, right? Positive y-axis. Let's deal just with S1 right now. So S1, we're trying to find the flux, right? Sorry, make that S1 down here because I'm doing the flux over S1. Now, there's something uniquely special about this problem that we haven't run into yet. And you know, on this formula here for the sphere, I said I skipped this one because the normal vectors on the sphere are always changing no matter where you are on the sphere. They're always different. For this problem on S1, do y'all agree that all these normal vectors are always the same? Because it's really a flat plane, isn't it? So what are the normal vectors there? Let me rewrite this. I can do this over S1 of F dotted with the normal ds. That's the formula that I didn't use before. But the normal vectors are what? You tell me. What do all the normal vectors look like?
0, 1, 0.
0, 1, 0. Because they're all pointed down the y-axis, aren't they? So if I take my vector field, right? If I take my vector field, so I'm going to continue this now. Double integral over S1 of my vector field. Now my vector field is 0, y, negative z. If I dot that with that normal vector ds, what am I left with?
Just y.
Y, right? Y ds. Now, this is a surface integral from before, right? Like from prior classes in this section. But there's something even better. There's something even nicer that's happening here. Do you all see it? When you're on that surface, when you're on this green surface, this disk, what can you tell me about y?
It's 1.
It's always 1. It says it right here, right? So y is always 1. Which means that this turns into the double integral over S1 of 1 ds. And can somebody tell me what that is? What that integral represents?
The area,
Area of what?
the disk.
Area of S1. That's the area of S1. Do you know the area of S1? Just by looking at it, do you know? Well, it's this disk, right? X squared plus y plus z squared less than or equal to 1. So this disk is got a radius of 1, doesn't it? So the area of that should be pi r squared, but r is 1. So the answer to this is pi without any integration. That's kind of cool, huh? if you had tried it a different way, then you could do it a different way. It'd be much more work. What I'm trying to get you to see is that when one of your surfaces has normal vectors that are always the same, you might want to try this, because a lot of times things work out nicely, because you'll always have like zeros in two of your components, and then the other one will be a one. So it really kind of like gets rid of a lot of bad stuff from the vector field. All right, now we still need S2. Now S2, when we look at S2, look at the normal vectors coming out of this here. S2, do you all agree that Y is some function of X and Z? It looks like this one. It looks like our Y value is some function of X and Z because our surface is kind of like sideways, right? Sideways down. I have to look at it from this perspective, right? Like this. If you took the green out of here, do y'all see the paraboloid would just be a surface where Y is a function of X and Z? But my normal vectors are pointed, are they pointed down the positive way of Y? They're not. They're pointed the other direction in Y. So when I go to use this shortcut formula to calculate the flux, because my normals are not pointed out this way, I'm going to use this formula, but I'm going to make it negative at the end. So I'm going to change the sign. Does anyone have a question why I'm about to use this formula? Sure.
Nope.
Okay. So we need to know, what is the function? Do we know what this function is? The surface? Y isn't that right here? X squared plus Z squared? That was given to us. Hey, do y'all understand, just to be clear, do y'all understand why I'm not using the formula with the n and the normal vector? Do you understand why I'm not doing it for this one?
The normal vector changes.
That's right. So as you move around the paraboloid, the normal vector is changing. Where on S1, it was always the same. So we could just replace it with a nice vector, 0, 1, 0. Here, because the blue vectors are always changing, can't do that. But I'll use the shortcut. Okay, so this is where I'm going to be going here. So I need to know a couple of things here. Do we know PQR? Yeah, it's right here, right? I'm going to go grab that. So here's my PQR. And I need some partials. What's the partial of G with respect to X and Z? I'm trying to get these two pieces here. So with respect to X is 2X, and with respect to Z is 2Z. So let's try this double integral. Here it is. Double integral over D of negative P. So let's put the negative out in front now so we don't forget about it, because remember, we have a negative out here in front. So what is negative P for us?
0.
Negative 0 or just 0, okay, times partial of G with respect to X, which is 2X. That's all going to go away. And then we have plus Q. Q is just Y, minus R, which is negative Z, and then partial of G with respect to Z, which is going to be 2Z dA. This just becomes double integral over D, a negative out front. Where'd that negative go? It disappeared. Did y'all see that negative disappeared? The one I drew
Yeah.
a minute?
It just left.
That happened to me today in my pre-calc class when we were trying to solve a system of equations, and one of my plus signs went away and went back to a negative or something. And the whole like 30 minutes of work was gone because of one little stupid thing. Okay, all right, back to this. Y plus 2Z squared dA. Good. Okay, so can we leave everything the way it is right now? I mean, let's see.
You have to replace the y.
Yeah, so we have to remember now our function, right? G was a function of x and z, which means when we integrate, we should be talking about x and z in our limits of integration. So we can't have any y's in here. We have to replace them. So now I've got to replace that y with this function x squared plus z squared plus 2z squared dA, which is negative double integral over d of x squared plus 3z squared dA. Okay, we finally have this down to a double integral. And we need to figure out our domain, D. So where's D in the picture?
Would we convert this to polar?
Yes, exactly. We're going to project this paraboloid up against the XZ, right? Up against, look, I'm just going to draw in the back there. Up along the XZ plane, we've got the domain is back there on the XZ plane. And that's a polar region, isn't it? It's a nice polar region. So I'm going to make my switch over here. I'm going to let X be equal to R cosine theta. And let's let the Z be equal to R sine theta. We'll let theta go between 0 and 2 pi. And R go between, should be 0 and 1. Yeah, we know it's 1 because this green disk had a radius of 1. So the shadow of this over here on the XZ plane should have a radius of 1. And that's it. I should be able to do this now. Negative integral, let's go 0 to 2 pi, 0 to 1. Okay, x squared is r squared cosine squared theta plus 3 times z squared, which is r squared sine squared theta, r dr d theta. Remember, the r came from the fact that we went to polar. Unfortunately, I couldn't use the Pythagorean identity. X squared plus z squared is r squared. I couldn't use it here because I had a 3 in front of this. So that's it. There it is. That could be done. Let me see, did I do it? I didn't do it here. Okay. Equals ... Questions? So let's recap again. First problem, find the flux across a sphere. No way, this wasn't a special case. We had to grind out this formula here. Second case, okay, this was a function of x and y, right? So with special case, we used the formula, everything worked out. This case, we had two different surfaces, okay? We had to do S1, which we were able to crank out with the normal vector and made it nice and easy. And then we have to do this one with S2. And unfortunately, it's this integral. Let's go ahead and get this answer, okay? I actually need this answer for later. So let me crank this out. Well, let's let the computer crank it out for us.
I have a quick question.
Yep.
So, since we're dealing with two surfaces, but we're trying to find the flux, do we sum the flux up over the two surfaces
that's why I'm getting this one, because we need to add the two fluxes together here.
Okay, just making
And that's
sure.
why it was important to put that negative in front, because the orientation was backwards. Okay. So yeah, let me put this in first. What was it going to be? It's going to be r cubed and then times cosine theta, but I need to square that, I think, yeah. And then it was plus 3r cubed times the sine theta squared dr dt. Shit, what happened? Man. Okay, something is wrong with R has been assigned somewhere else.
I see what you did.
What I do?
So if you look, you have, oh,
No,
wait.
it's the problem is R is defined to be something by the system already. See, R is defined to be 0. I need to clear R from the memory. Yeah, don't worry about it. I just use different variables. So our answer should be pi.
No negative?
Oh, did I forget the negative value? Yeah, sorry. The integral's answer is pi, right? So now we come over here. So this will be equal to negative pi. All right.
We just have pi minus pi.
Yeah, so when you do this, this gave us pi. So the flux out of the green side gave us pi. And then the flux out the backside gave you negative pi. And so the total flux, okay, the answer to this problem over the whole surface is 0. Okay. Find the flux of the vector field F equals x squared, y squared, z squared across the surface S, where S is the boundary of the half of the solid half cylinder. Z is between 0 and square root of 1 minus y squared, with x between 0 and 2. So this is the x-axis. We start back at the origin and go out to 2. That creates 2 sides, this front side and back side. And then we have the square root of 1 minus y squared creates the green part. And then the bottom of this thing is this rectangle. We want the flux across this surface, all of it, the whole solid, the whole surface of everything, which means we're going to have how many surfaces?
4.
1, 2, 3, 4. Yeah, 4 surfaces.
I have a question.
Yes.
For this like half cylinder, would the blue face and then like the surface on the back of this that kind of looks like the blue face, would they just cancel out or something? Would they be double?
Maybe. It depends on the vector field.
Okay,
Yeah,
Like
it all
in like
depends
a-
on the vector field.
I feel like in a constant vector field like the other ones that don't have like polynomials in it, it would have.
Yeah, maybe. I think here they're not going to cancel out.
just hoping to make it easier. Guess
Yeah.
not.
No. So, all right, let's label some things. I'm going to go in kind of the order I think that these can be handled. So this one right here on the front, let's call it S1. Let's call the one on the back side S2. Let's call the one on the bottom S3. And let's call the green surface S4. And remember, this x-axis comes out to 2 here, right? That's where we are at 2, and then the back side S2, where S2 is 0, right, for x. All right, let's start with S1. So when we're talking about S1, we're trying to find the flux over S1 of F dot ds. Okay, what's good about S1?
It's flat.
It's flat. And when we're talking about flux, when we have an enclosed object like this, we are going to assume positive orientation. So all our normal vectors need to be pointing away from the inside. So when I'm looking at S1, my normal vectors, I'm looking at them as pointing out down the x-axis. And since it's flat, the normal vector is always the same, right? So I'm going to be using this formula. Surface integral of F dot N d capital S. which should equal this double integral over S1 of F, which is my vector field, x squared, y squared, z squared, dotted with the normal vector. And what's that normal vector for S1?
If it's
One.
1, 0, 0.
1, 0, 0. And so this just becomes surface integral over S1 of x squared ds. Yeah? But
This one, x equals 2.
yeah, on surface 1, this flat surface, the x coordinate is always 2, right? Because you're on this little circle, but you're always on that plane, x equals 2. So because of that, this becomes 2 squared, that's 4 ds. And this is because x is equal to 2 because of where we are, right? And this is just 4 times the surface integral over S1 of 1 ds, which is 4 times the area of S1. Carefully, what is the area of S1?
Is it also pi?
The radius
pi
is
over
1,
2.
right? The radius is 1,
Oh,
right? But it's half of a circle. It's not the whole circle. So the area of that should be half a pi, right? So 4 times half of pi, which is 2 pi. Does everyone understand area of S1? It's a semicircle with a radius of 1. So the area should be pi r squared. So it should be pi, but we're only dealing with half the circle. So the flux out the front side is 2 pi. Let's try the S2. Okay, on S2, let's just clarify this from the beginning. X is 0 here, isn't it? On the back side, X is 0. Also, what can you tell me about the normal vector? The normal vectors. Now, be careful here. They have to point out the back away from it, right? So they're pointing like that direction.
So it's negative 1, 0, 0.
Negative 1, 0, 0. So if we want to do the surface integral over S2, or sorry, the flux over S2 of F dot ds, we're going to make this double integral over S2 of F dot n d capital S, which for us is F x squared, y squared, z squared, dotted with negative 1, 0, 0. But that's just this S2 of negative x squared ds, but x is 0, right? So this just becomes, and that is just 0. So we have no contribution to the flux off the backside. Moving on to S3. S3 is the bottom, right? The ground, that's z equals 0. Right? That's the plane on the bottom. Now, what about the normals for that one? Which way are they pointed?
Pointed down.
Straight down, right? The normals off this back side are pointed straight down. Straight down. Straight down. Right? Off of that plane on the ground. And that's 0, 0, negative 1. So normals are 0, 0, negative 1. So if I try and do the flux over S3 of F dot n ds, this is the x squared, y squared, z squared, the field, dotted with 0, 0, -1, which is just going to give us negative z squared. When you dot these. But what's z?
0.
0, 0. Why did I put S1 again? I'm sorry. It's S3. 3, 3, S3, 0, DS, which is 0. Okay, so no contribution to flux off the bottom. Last surface, S4. So when you look at S4 and you start looking at the normals on S4, they're changing, aren't they? So we can't do what we've done for S1, S2, and S3. So we're probably going to need the other formula, but S4 is a function of two variables, right? It's a surface. What is this surface here? Z is g of x, y, which is, what is the function?
Square root of 1 minus y squared.
Square root of 1 minus y squared, right? It's this half cylinder right here. All right, so I'm running out of room here. So I'm going to have to copy this, take it over to a new page. Okay. Oh shit, no, I don't want that. Okay, it's not letting me change the size here. Okay, so here we go, S4. So unfortunately, the normal is changing, so I'm going to have to do this. F dot ds, but that by definition is the double integral over d of f dot r, sorry, no, special case, right? We're doing our special case. The special case is z is a function of x and y, so we're doing h here again, or sorry, f. We're doing f, formula f, because z is some function of x and y, so this is the thing I'm going to use. Does it seem a little overwhelming, all these different formulas and cases and everything else? I mean, seem like a lot to have to kind of make sure is organized in your mind.
It seems like there's a bit much, but if we get to like use these formula sheets for the exam, then I think it's not that hard as long as we check that the conditions match.
Yeah. P, Q, and R are given here. P, Q, and R. Oh, you know what? I didn't mention this. I'm going to use this formula. Am I going to have to put a negative sign in front?
No.
No, because my normals are coming up off the top, right? So in the Z component is positive. If for some reason that cylinder we were on the bottom side of it, then we would have to still use the same formula, but change negative, put a negative out front. I don't have to worry about it in this case. I do need some partials. Partial G with respect to X. Oh, crap. Okay, partial G with respect to X. That's actually 0, isn't it? Partial of G with respect to Y, though, that actually kind of sucks. We have to take derivative of the square root of this thing, right? So I trust you can do that because you all passed Cal 1. All right, derivative square root of something. 1 over the 2 times square root of that times derivative of what's inside. You should get that. All right, we're going to keep going. So negative P is going to be negative x squared. That's your P's there. Times the partial G with respect to X, which is 0. Minus Q is y squared. Times partial G with respect to Y, which is this. Negative y over the square root of 1 minus y squared. and then plus R, which is Z squared, dA. I'm gonna move this down so I have a little more room. Double integral over D. All right, I should get y cubed over the square root of 1 minus y squared plus, okay, so that went away. Negative and negative is positive. Y squared and y became y cubed up on top. And then z squared, I can't have a z in here because my original function is a function of x and y. So I need to solve for z here. If z is this, then z squared should just be what's underneath the root. I think that's a pretty okay looking thing, I guess, not too bad. I need to figure out my limits of integration. Those are my restrictions on x and y. So that's the ground, isn't it? Hard to see it here, but that's the ground right there, which we should be able to tell from the information we're given. X is stuck between 0 and 2. That's from here to here. So x is between 0 and 2. And the y is stuck between -1 and 1 because this cylinder has like a radius of 1. We could tell from here. And so the y values have to go from -1 to 1. So I think we're almost to the integral now. 0 to 2, integral -1 to 1. Y cubed over square root of 1 minus y squared plus 1 minus y squared dy dx. All right. Now, we have to integrate that. I'm not going to go through it, but these two pieces are easy to integrate, right? This one's a little troubling, but the way you could do that is just rewrite it as y squared over square root of 1 minus y squared and put the other y out the back like that. And then just make a basic U substitution. U is 1 minus y squared. If you do that, then you'll be able to rewrite all of this and it'll work out nicely. All right, I'm not going to go through it, but this is something you could do. You could also use trigonometric substitution. Trig sub would work here, but it's a little longer when you do it that way. I'm going to cheat, and I'm going to use the computer because I'd like to know the answer. So far, what are we at? Are we at 2 pi? Is that where we are for the flux on this so far? We had 2 pi off the front side, 0 off the back, 0 off the bottom, and now we're looking at the flux across this cylinder. 0. I didn't do this one earlier. Oh, I did do this earlier. Okay. Here it is. Save us some time. If you do this integral, you get 8/3. So this equals 8/3. And so the final answer to this is that the flux over the entire surface of this field dot ds is equal to 2 pi plus 8/3. All right, let's take a look at the review for the final. Well, I'm not done for the day. I want to see, have we gained any ground here today? So last time I said you'd stop at 17, right? So let's look at 18 now. Find the flux where S is the part of this paraboloid which lies above this. Wait a minute, is that the problem we just did?
Yeah, it
What?
is.
It looks mighty close, right?
No, that's exactly what it was.
Yeah, so I would not look at your notes and see if you can do this, like, see if you can do this problem. Very unlikely you'll see this on the final, because I've done it already. All right. Okay, how about this one? Find the flux of the vector field F. Here's the vector field. And I want it just across these two surfaces, S1 and S2. Not the whole thing, just those two surfaces. So you should be able to do this now. Okay, so 18 and 19 are doable. 20 is not, 21 is not. 21 is, 22 is, 23 is, okay. So I want to get to a point where you can do 21, 22, and 23. Give me just a second. I'll be right back. And we'll do those, okay? Take a little. Okay. So I wasn't quite sure how much time that was going to take me today. Took me a little longer than I was hoping. So what I'm going to do is I'm going to skip 13.8. I'm going to go to 13.9. So let's talk about 13.9. This is the almighty divergence theorem. All right, also known as Gauss's theorem. So let's just take a look at the theorem first, and then we'll try and wrap our heads around how awesome it is. Let E be a simple solid and S be the boundary surface. Let S have positive orientation. In other words, the normals are pointing away. Let F be a vector field whose component functions have continuous partial derivatives on an open region. That just means we can look at the vector field, we can take partial derivatives. Then we have this. Okay. Let's see what this means. Okay, so if it says, if we have a solid, okay, so I'm going to draw a generic solid here. Okay, we call this solid E, all right? If E is a solid and S is the surface that goes around this solid, so it encloses E, then the flux, okay, the flux over the surface is equal to the triple integral over the solid of the div of f. This very important theorem says that if you want to know about the flow through the surface of the outside of something, right, then what you need to do is calculate the sum of the div. This is a triple integral is going to basically take a sum at every point inside the solid, but not of the field, it's going to be of the div of it. And div, remember, divergence is a measurement. It's divergence, if you remember when we were talking about divergence, well, curl, right? Curl was twist, right? Twist. Divergence was like this microscopic little flow out of each point or into each point. We had this idea of like a source or a sink. So somehow, if we want to know the flow on the boundary of the solid, we need to add up all of the infinitesimal divergences within the entire solid that it encloses. It's a fabulous theorem. Now I want to show you it in action, all right, because it's freaking awesome. So we're going to go back to this problem right here. We just did this problem, remember? We had surface 1, surface 2. We calculated that the flux of this was 0, but the way we did is we broke down S1, we got pi, then we did S2, we had to do a special case, and we did all this, right? Okay, I'm going to do the same problem, but now I have the divergence theorem. All right. And I'll do it right here. So here it is. We want the flux, right? So we're trying to find this. And what we need in order to use this theorem, this is critically important. We need that this surface S encloses a solid. It has to enclose a solid. And in this case, S is the entire surface, the green and that brownish color. So that surface together, S1 and S2, do enclose a solid, don't they? The solid they enclose is inside this thing. So what we're going to do is we're going to try and see if the divergence theorem helps us. We're going to try and do the triple integral over E of the div of f dv and hope things get better. So in order to do this, we have to know the div of f. Now the div of f was super easy to compute. It's way better than curl of f. Div of f, all you do is you look at the components, P, Q, and R, and you just individually go one by one and take the partial with respect to X, then Y, then Z, and just add them together. So what would be if we call this P, Q, and R, the formula is this: partial with respect to X of P plus partial with respect to Y of Q plus partial with respect to Z of R. And for us, that would be what? Partial of P, well, that's 0. Plus, what's the partial of Q with respect to Y? 1. Plus, what's the partial of R with respect to Z? So what do we get here?
-1.
-1. And when we add all those up, what do we get? 0.
0.
So the triple integral over E of 0 dV, well, shit, I don't need to know anything about E. That's 0. We're done. V, you're shaking your head.
It always seems easier on the back end.
Yeah, well, this theorem is super, super awesome, right? Because it allowed us to do that with no work.
There's always some theorem in math that seems to do that.
Yeah. Hey, do y'all remember what it meant for a three-dimensional vector field to be conservative? What had to happen for it to be conservative?
The curl was always 0.
0 vector, yeah.
I think it had to be incompressible.
Yeah, so that's where we got the, well, irrotational. Incompressible is when div is 0. So look at this. I guess what I'm getting at is this. If your vector field has a div of 0, right? Then the flux through any closed surface, right? Take any closed surface in that vector field and it's going to be 0 flux. Does that make sense? Like, give me any vector field where the div is 0, and I promise you that if you put a surface in there that's closed, the flux is automatically going to be 0 because of this theorem. Okay, let's do another problem. Which other problem did we do? Oh, we did this one just now, right? We had to break it into 4 surfaces. Okay, so do y'all see the solid in here that it encloses? Yeah. All right, so let's try this. We're going to try and do this flux by doing Gauss's theorem or the divergence theorem, and we're going to hope that the div of f is something better. So let's calculate div of f. All right, in this case, it's not as nice as the previous one, right? It's what? 2x plus 2y plus 2z, right? Not as nice as the previous one. But we can do this triple integral over e of, let's bring a 2 out, x plus y plus z dv. Look, this is a good old-fashioned triple integral. This is nothing crazy, okay? This is, well, crazy, it's a triple integral, all right? But it's like when we were first learning about triple integrals. This is what it is. So we just need to somehow figure out if we can find a way to represent E. So E is this whole solid, everything here, right? Well, there's kind of an easy way to represent that solid, I think. I can tell you that the x's are between, let's see, where did the x go between? It's back and forth here between 0 and 2, right? The y's were between -1 and 1. And what about the z's? What were the z's between?
0 and the square root of 1 minus y squared.
There you go. That's it. So it may not be pretty and perfect, but here's what we've got. We've got our x's go from 0 to 2, y's go from -1 to 1, z's go from 0 to square root of 1 minus y squared, and we're integrating x plus y plus z with respect to z, then y, then x. Shall we? Let's do it. 2 integral 0 to 2 integral -1 to 1. Okay, antiderivative time. X z plus y z plus 1/2 z squared. So I did the antiderivative of each of these with respect to z. I'm evaluating that from z equals 0 to z equals the square root of 1 minus y squared. After I'm done with that, I'll go dy and then dx. Two integral 0 to 2 integral -1 to 1. Okay, when we plug in, we get x square root of 1 minus y squared plus y square root of 1 minus y squared plus 1/2 times 1 minus y squared, because we're going to square the square root and it's going to go away. And we got that. Now with me? Equals 2 integral 0 to 2 integral -1 to 1. Okay, antiderivative of this with respect to, oh, not yet, with respect to y. Okay, what's the square, x is a constant. What's the antiderivative of the square root of 1 minus y squared? Ooh, well, maybe we just go back to our formulas from Cal 2. See, do we have a formula for that? 1 minus y squared. Do we have it? It's not on here, is it? Dang it. I was hoping to do a short way, but I guess we'll just do it the good old fashioned way. Okay, I'm gonna have to come back to that, I think. How about this one? Can you do this one? Do y'all see just a basic U substitution? U is this. Yeah. And derivative that's out here. Man, I'm wondering if I should go through this whole thing. I mean, we can at this point, but I'm looking at the clock and I'm like,
You're not going to want to. I just did the integral for 1 minus y squared, or the square root of 1 minus y squared.
did you do trig sub?
Yeah, it doesn't turn out nicely.
No?
It becomes, well, 1/2 arc sine of x plus 1/2 sine of 2 arc sine of x.
Yeah, so I think that might be an ugly integral. Well, let's do this. Let's do this. Because of time constraints here, let's put this into our,
What if you switch the order of integration?
that might help. That might help. But I don't think you're going to get away from, you're going to have probably an arc sine or something in here. At some point, you won't be able to avoid it. Okay, so I think on the first example I gave you here, you're like, yeah, everything is awesome, man. And then you're like, oh, well, wait a minute, this is good, but I mean, is this integral really that much better? You know, I think this is doable. Let's get the answer so that we have it.
Well, the other one was longer, but it was an easier integral.
Yeah. So this goes 0 to 2, this goes -1. Oops, -1 to 1.
I'm wondering if it was possible we could have converted to cylindrical coordinates.
Yeah, on the project it down to the YZ plane instead.
Mm-hmm.
Yeah, that might have been a good approach. I actually like that idea. Yeah, let's do this. Maybe we will. 1 minus y squared. And then it was x plus y plus z dz dy dx. Oh, I forgot the 2 out front. Hey, isn't that 8/3 plus 2 pi? Same answer that we had the other way. I actually really like that idea. I really do like that idea. Instead of doing this, I don't know, we'll do it in red. Instead of doing our region like this, why don't we do it this way? We say that the x is between 0 and 2, right? But then now we're going to make the y, I'm making the y equal to r cosine theta and z be equal to r sine theta. And now theta and r. So I'm projecting this onto this back plane, and that's going to be my region. X is between 0 and 2, but the shadow on the ground is a half circle. So theta should go between 0 and pi. I'm just trying to see if this is any better. Between 0 and pi, because we only want half the circle, and the radius goes between 0 and 1. See if it makes it better. I don't know if it does. 2, 2, 3, let's go 0 to pi, 0 to 1, 0 to 2. This is where things are going to get weird. We're going to have x, which is r cosine theta, plus y. What's y for us?
No, x is
Sorry,
x.
x is not x. X is x. Y is r cosine theta. Z is r sine theta. We have to hit all of those with r, right, for the conversion. And then we have d.
But
dx.
doesn't that actually just become a trig substitution?
No,
Sorry, trig
No.
identity with r squared theta plus r sine theta. That would just become r squared, would it not?
because that's just cosine and sine.
Yeah, we don't have this, the sine and cosine aren't squared, unfortunately. That'd be nice if it was. But this integration isn't bad. I actually like this. I want to continue. Okay, so now let's do 2 integral 0 to pi, integral 0 to 1. Okay, antiderivative with respect to x first, 1/2 rx squared plus r squared cosine theta x plus r squared sine theta x, evaluated from 0 to 2, dr d theta. And when I plug in 2 for all of my x's, all of my x's. All right, when I plug in 2, what do I get here? So 4, half of that 2, so 2r plus 2r squared cosine theta plus 2r squared sine theta dr d theta. Now antiderivative with respect to r is going to be r squared plus 2/3 r cubed cosine theta plus 2/3 r cubed sine theta,
Make it a little
evaluated.
easier and take that 2 out of the first one, couldn't you?
Oh, from here in the very beginning?
Yeah,
Yeah, I mean, yeah, it could have come out. R equals 0 to 1. Okay, so when we plug in 0, everything's gone. When we plug in 1 for r, we get 1 plus 2/3 cosine theta plus 2/3 sine theta d theta. We're almost there. 2 pi, antiderivative now is going to be theta plus 2/3 sine theta minus 2/3 cosine theta, evaluated from 0 to 2 pi. When I plug in 2 pi for theta, I get 2 pi.
should just be 1 pi.
Pi, yeah, what did I do? I did, that's pi, thank you. It's pi. So when I plug in, I get pi here, plus, okay, what's sine of pi?
0.
0. Cosine of pi?
-1.
Negative
1. So it'll become plus 2/3 there, right? And then I subtract from that what I get when I plug in 0, which will be 0 here, 0 here. And then cosine of 0 is 1, so we get negative 2/3 there. So we get 2 pi. Wait a minute, where did that pi come from? Where did
Just
this pi
decided
come
to
from?
add that. That's
Where
the
did that
point.
pi come from?
It didn't come from anywhere, you just added it.
Yeah, that's just a 2. Here it is. Pi plus 4/3, which is 2 pi plus 8/3. All right. Good, I like that, Daniel. That was a good idea. Yeah. That's just a better way to, well, not a better, this integration could have been done. I probably would have been done with this already by now, maybe, who knows?
Yeah, but it looks
Okay.
nowhere near as nice.
Yeah, it's definitely not as nice. So if we go back to the review. Okay, number 21, find the flux across the surface. And this is a cone. Okay, so that's a cone that looks like this, where z is between 1 and 3. So the bottom is, oh, it's not quite like that. Hold on. It's more like this. Okay. So find the flux across this surface S, where S is this cone. It's just the cone, it's not the two caps. It's just the cone. You have no choice but to go and do this the hard way. You cannot use the divergence theorem because your surface is only this outer side. It's not including this top piece and bottom. If it had the top and bottom, then you can use divergence theorem. That's the drawback to divergence. You have to have an enclosed solid. Now, if you look at number 22, find the flux. Here's our surface, all faces. Can you use divergence theorem?
Yes.
Absolutely. How about number 23? Find the flux.
Yeah.
You can use this, right? S is the surface of the solid. So it's all of the surface. And we said, don't worry about 24. So you can do 23. You can do 22. 21's going to be rough, but it can be done. Okay, 21 and 20. We just didn't get a chance to talk about.
Do we have two 21s?
Is there two 21s?
Yeah, we saw that last time.
Yeah, okay, so yeah. So of this one right here, this version of 21, these two, we didn't get to. That's the section I skipped, 13.8. So here's what I'm gonna say. Remember, mini exam 7 is this review turned in, right? You've worked through the problems. Except for this, the first number 21 and number 20. You don't have to do those. I'm not worried about those. However, if you go and watch my lecture on this, I'm going to actually send it to you in the chat just so you can have the link to the video.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct, but it's wordy and hard to.
Okay, so this actually starts, hold on, I got to get to where it starts.
Y squared. Get around that is if you don't. We did a comment presentation for each of. I have to make it before I can tell you.
Okay, here we go. Okay, so this link should send you exactly to that moment in the lecture when I start doing Stokes' theorem. If you watch that, there it is. If you watch that and then go complete these two problems separately, okay, so this would, you're going to do mini exam 7, you turn in your review. Mini exam 8 will be numbers 20 and 21 done on separate paper, which means you have to go watch the video and learn it and understand it and try and do it. Okay.
You didn't post the link.
I didn't? Oh, I just sent it to one person. Sorry. Only Adam gets it. There we go. Okay. All right, so at this point, I mean, we're there, we're at the end. I'm going to send out an email in the next day or two because next week my office hours are not normal because I'm in different places giving tests and stuff. So expect in the next day or two for me to give you like a layout of when I'll be available. And I'm going to try and make myself available a few times during the evenings in the next, you know, maybe even over the weekend. If you have any questions you want to come discuss with me, we can. Tomorrow, normal office hours though. Okay. Yeah, is there anything else?
We're not meeting on Monday, right? No meeting?
No, we don't meet on Monday. It's finals week, so you should only meet once with your classes. And I really do appreciate all of your attendance and participation. You know, it's this is hard to do. Zoom Cal 3 is really tough to do. I'd rather be in the classroom where I can walk around, and usually I have like yardsticks and stuff so I can have vectors and directions. And, you know, by the end of the semester, the classroom, everyone can see the classroom is like the x-axis, y-axis, z-axis. And this is hard. So I actually appreciate everybody hanging in there with me with this and getting through the snow vid and all that stuff. And the fact that we even came close to finishing is amazing, but I was rushing here at the end. I really had to, but all right, well, I think that's it, unless you've got anything for me.
Sir, just real quick, the final is just going to be through Zoom?
Yeah, just come here next Wednesday at 12:30, right? 12:30, not 1. And I will tell you, hey, you know, from this review, I want you to do these problems. And so the idea is if you can do the review, then you'll be fine on the final. Okay, but that means you do the review, not like you have all the answers here and then during the test you're looking at your answers. Work them all out, and then test time, you put everything away and have it come from here. Okay.
Yes, and thank you for everything as well. Bet it was hard for you too for grading all of us, you know, staying at home as well.
Yeah,
Kind of
no, I
boring.
mean, we're going to be back in the classroom at some point, you know, soon, hopefully. And, you know, I'm glad that we have at least the technology to do something like this, because, you know, 5-6 years ago, I don't think we'd be doing this. I'm not sure we would have this.
I think we'd all be sitting in a classroom hoping we didn't get COVID.
Yeah. So, yeah. So, yeah, for most of you, this is probably it. Like, you know, I probably won't see y'all again in another math class down the road. A lot of you are going to transfer out to another university. So I will, as I do with all my students, I always say, you know, my door is always open to you. You know, even if you go off to another school and you want to reach out to me and you have questions or just want to kind of keep me up to date on how things are going with you, you know, I'm always happy to hear from my former students, see how they're doing and stuff. So, you know, my door is open to you. All right, study hard. Good luck on all your other finals.
Thank you, Professor. It's been an honor.
Yeah, well,
Thank you. We'll probably
Yeah,
see you
thank
tomorrow.
you.
I'll see you soon.
Thank you.
Yeah.
Yeah,
Appreciate all the help.
okay, y'all have a good one.
You too.